Sorry about that. You must be Harry. Did you know you're a mathematician? I'm a what? A mathematician, and probably a good one if you study a little.
Don't go filling his head with those crackpot ideas.
Shut up, you muggle! He will be going to the Hogwarts School of Curves and Surfaces. He will be taught by the finest mathematician called Abacus Number Maths. You coming, Harry? Hi, I'm Harry Potter.
You're Harry Potter. I'm Hermione Granger. And you are?
I'm Ron Weasley.
I've already been reading my textbooks. I know all about curves. Did you know that a map is called smooth if it is arbitrarily often differentiable?
How did you know that?
Books, Harry, books. I also know that a curve is a smooth map.
Oh, I didn't know that.
I also know that the differential of a curve is called the tangent. I'm leaving. You two should change into your robes. When I call your name, you will come up and the sorting hat will sort you into one of the 4 houses. Gauss, Noether, Newton or Euler. Hermione Granger, calm down. It'll be fine. Don't worry about it. It'll be fine.
I know that one. I'm telling you.
Gauss.
Draco Malfoy.
Noether.
Great mathematician who's gone mad who ain't been in Noether.
Susan Bones.
Euler.
Ronald Weasley.
Ah, another Weasley. Aha. Gauss.
Harry Potter.
Not Noether, not Noether.
Not Noether, eh? Well then, better be Gauss.
Welcome to your first class. I'm Professor McGonagall and we're going to be talking about plane curves. We will call a curve regular if gamma prime is not equal to 0 for all t in the open interval on the real line. If this is not the case, we will call the curve singular. If a curve is regular, then it is possible to reparameterize it by unit speed. To check if a curve is unit speed, we find the norm of gamma prime. If this is equal to 1, then the curve is unit speed. If this is not the case, then we must reparameterize to unit speed. To do this, we must follow these 5 steps. Firstly, we check that the curve is regular. If the curve is not regular, then it cannot be reparameterized to unit speed. Secondly, we find the arc length function, which is the integral between t and t0 of the norm of gamma prime. We call this S. Now we calculate phi of t, which is the inverse of S. We then find the composite of gamma and phi, which gives us our reparameterization by unit speed. Finally, we must check that this reparameterization is in fact unit speed. Curvature. For a unit speed curve, the curvature is defined as kappa is equal to the norm of gamma double prime. However, if a curve is regular but not unit speed, then the curvature is defined as the determinant of gamma prime gamma double prime divided by the norm of gamma prime cubed. It is also true that kappa of phi is equal to kappa of the reparameterization by unit speed. The side curvature of a regular curve is defined as kappa s is equal to the modulus of the determinant of gamma prime gamma double prime divided by the norm of gamma prime cubed. That is the end of our lesson on plane curves. You may leave.
There will be no foolish statistics or silly algebraic topology in this class. I'm Professor Curvius Snape, and I'll be teaching you about space curves today. As we've already seen, a map gamma from an open interval on the real line to R2 is called a plane curve. A map gamma from an open interval on the real line to R3 is called a space curve. For a unit speed space curve, the curvature is defined as kappa is equal to gamma double prime norm. For a regular space curve, the curvature is defined as kappa is equal to the cross product of gamma prime and gamma double prime normed over gamma prime normed and then cubed. A regular space curve, gamma, is called a Frenet curve if its curvature kappa is nowhere zero. The Frenet frame TNB of a unit speed Frenet curve is given by the tangent T is equal to gamma prime, the normal N is equal to gamma double prime over the norm of gamma double prime, and the binormal is equal to the cross product of the tangent and the normal. The torsion of a unit speed Frenet curve, gamma, is defined as tau is equal to negative the inner product of the binormal dashed with the normal. A curve's torsion tells us how much it twists. Class dismissed.
Curve in the dungeon! Curve in the dungeon! Who would you want to know?
Hermione!
Oh no, it's a plane curve.
Ron, find out if it's regular.
It's not regular, it's equals 0. We've got to restrict the domain.
Restrict the domain then!
Okay.
Oh, it's not unit speed. Ron, you have to make a unit speed. Harry!
Ron, do something!
Make a unit speed!
We can't find the explicit parameterization, but we know it exists because it's regular.
Compute the signed curvature, Ron.
Okay, I have to find the first and second derivatives of gamma, and then the length of gamma prime. Okay. I've computed the signed curvature. Yay!
You visualize the curve.
Yay!
I'm Professor Lincoln. This is your class on surfaces.
A topological surface patch is a subset of R3 such that there exists a homeomorphism from an open subset U of R2 onto S. X is called the parameterization of X, and its inverse is called the chart of S. Further, if our parameterization X is smooth and the partial derivatives XU and XV are linearly independent, then we have a regular surface patch. A subset S of R3 is called a surface if for every point P in S there is an open neighbourhood W of P such that the intersection of W and S is a regular surface patch. Given a surface S and any point P in S, we define the tangent space of S at P as the set of all vectors in R3 such that there is a curve gamma from an interval into S such that gamma of 0 is equal to P and the derivative of gamma at 0 is equal to V. The first fundamental form of a surface S is the bilinear form sigma P that takes two elements V and W from the tangent space of S at P into R. It is defined as the inner product of the 2 points V and W. The coefficients of the first fundamental form with respect to parameterization can be calculated as the inner products of the combinations of the partial derivatives of X. The Gauss map of a surface S is a smooth map N from S to R3 such that N of P is orthogonal to the tangent space S at the point P, and that the norm of N of P is equal to 1 for all points P in S. If a surface has a Gauss map, then it's called orientable. For a smooth map F from S into Rm, we define the differential of F at the point P in S as a linear map dFP from the tangent space of S at the point P into Rm, given by dFP of W is equal to the derivative of F composed with gamma evaluated at 0. Here gamma is a curve on S such that gamma at 0 is equal to P and gamma prime of 0 is equal to W. For a surface S and a Gauss map N, the second fundamental form of S is the bilinear form tau of P, which maps two elements of the tangent space of S at P into R. defined as minus the inner product of the differential of n, p at v with w. The coefficients of the second fundamental form with respect to the parameterization x are given by the following. If the Gauss map n is given by the parameterization, i.e. n is equal to n cross composed with the inverse of x, where n cross is equal to the unit length vector given by the cross product of the partial derivatives of x, then we can write the coefficients of the second fundamental form as the inner product of n cross with the second partial derivatives of x. We define the shape operator as the self-adjoint linear map AP from the tangent space of S at the point P to itself as APV is equal to minus the differential of NV. The eigenvalues kappa 1 and kappa 2 of the shape operator are the principal curvatures of the surface S. From this we define the Gaussian curvature as the product of the principal curvatures and the mean curvature as the mean of the principal curvatures. If gamma is a unit speed curve on the surface S and n is the Gauss map of S, then the normal curvature of gamma is given by the inner product of n composed with gamma and the second derivative of gamma. The geodesic curvature is defined as the inner product of the cross product of the derivative of gamma with n composed with gamma and the second derivative of gamma.
Professor Snape will be way ahead of us now.
We must hurry, we have to stop him.
Space curve! There's a space curve!
Calm down, Ron. We know how to defeat a space curve.
How do we defeat the space curve?
First, we need to see if it's regular.
It's not regular, but we could restrict the domain.
If we restrict it to the positive reals, then it is regular. How about unit speed? Run!
We need to defeat the curve first. It's not unit speed. The norm of the first derivative isn't equal to 1, and we can't find the integral of the arc length function explicitly, so we don't know how to reparameterize the unit speed either.
But we can compute the curvature. We need to find the first and second derivatives of gamma. We take the cross product of them, and finally we divide that by the norm of the first derivative of gamma cubed. But what about torsion?
Torsion. Inner product of the first derivative, cross product with the second derivative, and then third derivative of gamma.
Divided by the norm of the first derivative cross-producted with the second derivative squared.
So we know how it curves, and we know how it twists. We can draw the space curve. Look, we visualized the space curve.
It's defeated! You know what, Harry? When we look at it from above, it looks just like that plane curve we defeated before.
Yeah, it's because the first two component functions are the same.
Oh, right. What are we going to do about Ron?
Take him off to the hospital wing and let Abacus number maths know where I am and that Snape is trying to get the stone.
Okay. Good luck, Harry. You're a real good mathematician, you know.
But I've shown that X is a surface patch when restricting to an appropriate domain, and I still don't have the stone.
Compute the coefficients of the first and second fundamental form, fool!
Aha! Oh. Aha! I still don't have the stone!
It's you! But I thought it's Snape!
Yes, no one would ever expect poor stuttering Professor Quirrell, would they?
Snape let the curve out.
You fool boy. I let the curve out.
Use the boy! Get the stone!
Boy, come here and compute the Gaussian and mean curvature. Now!
Gaussian and mean curvature. Oh.
Let me speak to the boy!
Alright.
Boy, give me the stone!
Never!
Get him!
I found normal and geodesic curvature as well.
Ah!
Professor Numbermat, why could I get the stone and Voldemort couldn't?
Well, Harry, that surface had mean curvature 0. That means it's a minimal surface. That means that at every point on the surface, the principal curvatures cancel each other out. That means that every point acts like a saddle point. Famous examples of minimal surfaces include an Epps surface and the catenoid. When we dip a wireframe in soap, the soap film that's created can be modelled as a minimal surface. Only a true mathematician could have defeated the surface. You defeated Voldemort. Well done, Harry.